Thank you, Paul. I'm happy to be here, and thank you for committee inviting me to be here. JAXA is continuing to launch the advanced synthetic capture radar from the 1990s, and this is the third generation of the advanced SAR, which was launched May 24th this year, and we've been doing the initial calibration phase, and finally we have had the go sign to distribution of the SAR data November 25th. Then you can enjoy the data from this third generation of the advanced SAR. This ALOS-2 was approved in 2008. After that, we tried to complete the system for the launching of within 5 years. And through some critical issue, we finally succeeded to this satellite on the space. And this satellite has 4 mission objectives. One of that is disaster monitoring, because Japan is facing a lot of the disasters. And then we have the environmental monitoring using the advanced SAR has a very nice feature to monitor the forest. And also having the very nice feature of the penetration, giving the interparametric coherence. And combination of those two parameters gives us a very nice knowledge on the environment. This image was the first shot taken by the ALOS-2 June 19th this year, and giving the very nice picture of the island 170 kilometers south of Tokyo, showing the very detail of the island with 3-meter resolutions, and also gives a nice feature of the island with very nice, very low noise levels. This is a third generation, and having more improvement of the sensors, because the sensor performance is a key for the driving of the earth science. And this one table shows a summary of the feature of our Palsar-2, ranging from the high resolution of the spotlight to the fine resolution of the 28 megahertz, which is standard operation mode used by the ALOS, and also providing the 490 kilometers worth of the scanner L-band in dual polarization. So combination of the dual polarization of the and high resolution gives contribution to, I think, our science. And this is images taken from the initial calibration phase of the Palsar-2, which was done 1 month ago. This left-hand side image is standard 3-meter image, spotlight image, strip image, observed the Quebec City June 20th, and the right image is 28 megahertz. Main resource for monitoring of the globe using by this mode, observing the Mount Fuji area, and polarimetry is used for observing the forest in the Rio Branco, Brazil. And this is a new function added to the Palsar. This is a spotlight image, illuminating some area over the 30 seconds. Achieving the 1-meter resolution in the azimuth direction over the Kobe city, showing the very nice picture even over the ocean area, and also city structure can be visible. This is a comparison of the spotlight image left-hand side and 3-meter image right-hand side. If I zoom up the image, comparison of the image can be seen something like that. Left-hand image is a spotlight, 1 meter, and right-hand image is 3 meter. We can show the difference of the road running in just the center of the image, and 3 meter. There is a similarity, however, the spotlight gives better image identification. And this is a scan image of the 350 kilometers of Rondonia, famous for the deforestation area, in HH polarization. And the right image is dual polarization of the 490 kilometer image of some area in Brazil. And normally we use dual polarization of the image, and the difference of the HH and the HV is of the liver area. The double bands gives a white response, while the HV has no response near of that. And combinational use of the dual polarization can give the forest deforestation image. Some image from the calibration. This is the image of the corner reflector. Corner reflector is a very important instrument to check the quality of the image. This cross pattern is the response of the corner reflector, and this is a comparison of the loaded, just loaded. Sorry for the science. This is the engineering point of view. The Palsar has 6,000 watt of the transmission power, which is 3 times bigger than the Palsar, and also signal to noise ratio is almost 5 dB better than the Palsar, and this gives nice information of the observing the dark target. And we are checking the quality as well, and this is some toolkit of showing how the polarimetry works, and most of the polarimetry image always shows very nice this pattern, and also impulse response function gives a very nice picture of that. So that provides sensor performance itself is very good. And sorry for the very busy chart. And this chart, what this chart shows is there is a number of the criteria whether or not the sensor can be usable for the monitoring of the Earth. Roughly speaking, I think the sensor can be used for the monitoring of the Earth. One big thing I can tell you is the noise level is very small. This is a specification, and most of the mode shows 10 dB better than the specification. I think this can be used for the science. And for the after the operation of the after the launch of the satellite, we have collected almost 3 months for the normal operation from the August 20th. After that, we are accumulating the data. And this is one example of the application of the Palsar-2 data for the forest, non-forest detection. Those combination of the HH and the HB polarization can give us a pattern of the forest pattern in this Rondonia area, as we have done for the Palsar 2010 years. This is a differentiation of the forest, non-forest information given by our Palsar-2 and Palsar 210. Of course, Palsar area does not cover the total area yet, and those differentiation gives how the forest changes or recovered even the 4 years difference of that. And those on Rondonia area, we see the red area shows a decrease of the forest, and this means forest deforestation is in the way of increasing, preceding. And this is, I will skip this one. And this is an image made by the Palsar data showing the annual deforestation in Indonesia area, and we are going to generate Palsar-2 based forest information to know how the forest changes globally. This is deformation monitoring, volcano and earthquake using the differential interferometry. Palsar-2 has 14 days revisit time. Then, and also the orbit is maintained within the radius of 500 meters. Actually, it is within 250 meter diameter. And also the transmission power is increased to the 6,000 watt compared to the Palsar has 2,000 watt. Then better interferometry coherence is expected. This is one example of the subsidence of the volcanic mouth in, sorry for Japanese, very small island south of the Kyushu, and this was erupted early August, and using the 14 days separated data, we could see some subsidence occurred inside of the mouth. This seems to be 3 centimeter or 2 centimeter in that order. And also, very end of the September, this was September 27th, we had a very serious volcanic eruption at the Mount Ontake area, and using the interferometric processing, we could see this area is shifted to the west direction in the order of the 9 centimeter using this element interferometry. A coherence improvement of the pulsar was expected and required from the most of the scientific users. And what we did is shorten the revisit time and also the improvement of the transmission power. This is a 3-generation SAR change in terms of the coherence. JRS and Palsar-2, and this is 14 days. And as you see, the coherence is improved so much. This is a zoom up of the fringe in a near range of the Mount Fuji. This is the peak of the Mount Fuji, and we could see some fringe line is a continuous feature is remaining here. And we could make a digital elevation model. Even the altitude accuracy is less because of the perpendicular baseline. This case is only 250 meter or 300 meter. Maybe we need the stacking of the data. This is application of the sea ice. We've been almost observed the total area of the North Polar region using the scanner data. And using the scanner mosaic, we could see the open ocean and the high density of the sea ice, and also even we could see the SIP detection. This is, I will skip. And the SIP detection, this is very promising because of the noise equivalent sigma 0 of the Palsar-2 is 10 dB better than the previous Palsar. Then we see recognize the ship and also the wake of that, and application to the ocean will be very effective. And this is the first example of the interferometric processing of the Antarctica area. And there is a ice flow of the Antarctica. We need more time for the investigation. And just the example. And one thing is ALOS-2 is required to very urgent observation. And those 2 images was acquired within 12 hours after the volcano was erupted, and we have the data was acquired in 12 hours and processed very quickly, then showing the displacement or existence of the acid areas here, and appearance of the volcanic mouth was detected. However, there is some issue. Urban SAR is a lot of contaminated by the interference, and we need to integrate. We need to research how the temporal spatial distribution of the RFI characteristics. And the conclusion is that, and ALOS-2 is currently in a very good condition, and we are operating the Palsar-2 every day, and we are waiting for your use of the Palsar urban SAR data. Thank you very much.
Thank you. Are there any questions? We have time before you leave the stage. I'm sure there must be a question or two.
What measures are you taking to deal with the RFI?
So repeat the question, please.
Okay, RFI is when we are doing the we do all the processing. We process all the data, and during the processing, we apply the FFT, Fourier conversion of the raw data to detect which frequency is affected. Then we replace high spectral band by zero values, notch filtering. And the ratio of the zero replaced area is colored in RFI parameters.